Okay, in this video we're going to look at Chapter 18, the central limit theorem, and Chapter 19, confidence intervals. The central limit theorem is based on two assumptions, that the sample values must be independent and the sample size must be large enough. The mean of a random sample has a sampling distribution whose sample can be approximated by a normal model. The larger the sample, the better the normal approximation will be, and this is regardless of the shape of the population distribution. So what they're saying is if the sample size is large enough and the values are independent, it's pretty much going to, by the central limit theorem, work out to follow a normal model. Distributions of sample proportions. The population has a fixed proportion, which we'll call P. To find the population proportion, a sample is taken and a sample proportion, P hat, is calculated. If samples are repeatedly taken with the same sample size, the mean of the sampling distribution would be the same as the population proportion. So the mean of P hat would be equal to my population proportion if I took several samples of the same size. The standard deviation would be the square root of P times 1 minus P over N. And if we don't know what P is, then we would use P hat in its place. Conditions to check for the assumption. So I need to have a success and a fail. I can only have two outcomes. So N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10 to meet that condition. The second is the 10% condition, which is my population has to be greater than 10 times the sample. And randomization can be either stated, if it says it's a simple random sample, then we would just say simple random sample was stated, or we can make the assumption that the sample is representative of the population. If all conditions have been met, then we use the normal model of sample proportions. If the samples were repeatedly taken with the same sample size, then due to the central limit theorem, the distribution would be approximately normal. Okay, and then it'd be, when I write my normal model, it's the mean and the standard deviation. Alright, this example. According to the manufacturer of the candy Skittles, 20% of the candy produced is the color red. What is the probability that given a large bag of Skittles with 58 candies that we get at least 17 red? So, does it meet the conditions? Well, N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10, which they both are. Has to meet the 10% condition, so 10 times my sample size of 58, which gives me 580. Well, there are more than 580 Skittles in the population, so that will work. And randomization, it wasn't stated, so we're going to assume that the 58 Skittles in our sample are representative of all the Skittles in the population. Because it meets all these conditions, I can use the central limit theorem to say that it could follow a normal model with a mean of 0.20, that's my p-value, because they gave me the population proportion of 20%. And then my standard deviation is the square root of p times 1 minus p over n. Now that I know it's a normal model, I have the mean and the standard deviation, I want to know what's the probability that I get at least 17. So the probability that my sample proportion is greater than, or equal to, I guess, 17 out of 58. So that would give me 0.2931, which I could plug into my calculator. I'm using a normal CDF, and I would get 0.0381, so about 3.8%. Alright, your turn. We're going to do page 433, problems 12 and 16 in class, so save that. From chapter 18, distributions of sample proportions, P hat, follows this model if the checks pass. So I have a normal model with a mean of P and a standard deviation of P times 1 minus P over N. However, most of the time we don't know the population proportion, so we take samples to calculate p hat in order to try to find p. Since we don't know what p is, we can't find the standard deviation. So instead, I'm going to use p hat as an estimator for p. Then we can estimate the standard deviation with a new formula called the standard error. So standard error is just like standard deviation, except for instead of using p, I'm using p hat. Alright, so let's look at an example. It is election season. You open the newspaper and see the headlines. 57% of the nation favors the Democratic candidate for president. Does exactly 57% of the nation favor the Democrat? Why? Okay, well, no. Okay, this data was mostly collected from a sample, so it's not exact. B says, as you keep reading, you see the following. There is a margin of error of 5%. What does this mean about the true percent of the nation that favors the Democrat? So a margin of error of 5% means plus or minus 5%. So I'm going to take 57% plus 5%. And I'm going to take 57% minus 5%. So it's 62 and 52. So that means that the true percent of the nation should be between 52% and 62% that favor Democrats. As you keep reading, you see the following. The results of this poll are given with 70% confidence. Do you think their results are reliable? Okay, so no, 70% confidence is not very high. Okay, so you want to be closer to 90, 95, 99%. Those would be more reliable the closer you get to 100%. What if they change the confidence to 95%? Do you think their results are reliable? Why? So yes, at 95% confidence level, you have a much higher chance of capturing the true percentage. What if the results are as follows? 57% will vote Democrat, margin of error of 15%, with a 99% confidence. What can you say about the results? So we would say that we are 99% confident that the true proportion of people who would vote Democrat is between 42% and 72%. Alright, the basics of confidence intervals. So it's based on p hat and the sampling distribution of p hat. So we're going to start with p hat and give ourselves a margin of error on either side. The size of the interval, which is the margin of error, is based on the sample size and the level of confidence. So if I have a larger sample size, I'm going to have a smaller interval and it's going to be more accurate. If I have a larger confidence interval, I'm going to have a larger or wider interval, and I'm going to need more room for error. So I'm going to have a larger error. The basic setup is your estimate, which is p hat, plus or minus your margin of error, will give you your two values, your lower value and your upper value. So this is specific to a one proportion sample. So what we're going to be doing is a one proportion confidence interval. So Z star is an important piece. So we'll have to, this is the formula, so it's p hat plus or minus Z star times the square root of p hat times 1 minus p hat over n. Z star times the square root of p hat times 1 minus p hat over n, the standard error. That together makes your margin of error. Z star is the critical value, and we'll talk more about that in future slides. Okay? So 3 main confidence levels. So these are some of the more commonly used confidence levels, and their Z star values, so you might want to refer to those or have those memorized. It might be a little bit easier, but you can calculate them on your calculator in case you forget them. So other confidence levels. How do we find Z star if the confidence level is not 90, 95, or 99? Okay, so I have a confidence level, let's say, of 92%. So I have 92% in the middle. That would leave me a 8% total, which would be 4% above and 4% below. So I would use the inverse norm in my calculator to get the Z star value. So I'd use inverse norm. I'd plug in 0.04 for 4% with a mean of 0 and a standard deviation of 1. And that would give me the Z star value to use. So if my confidence level is 92%, my Z star would be 1.751. And don't worry if it's positive or negative. It's just talking about the direction. All right, sentence interpretation. So you're going to always kind of write the same sentence when you're working with confidence intervals. So we would say, we are blank % confident that the true percent of whatever it is we're talking about is between blank and blank %. Okay. The conditions you're going to check is n times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. My population has to be greater than or equal to 10 times the sample size, and it has to be a simple random sample, or we have to assume that it's representative of the population. If all conditions are met, then we can say that p hat has the model of a normal model with a mean of p hat and a standard deviation of p hat times 1 minus p hat over n. And we can use the normal model for a 1 proportion Z interval. So that's what we're doing. So our first example, our next example, we want to know the real improvement rate for new medication. We conduct an experiment to find that out of 53 subjects, 27% of them report improvements with the new medications. Create a 95% confidence level and interpret. So before I start anything, I'm going to identify my variables here. So I have 53 is n. My p hat value is 27% because that's coming from the sample. And I want to do a 95% confidence interval. I need to check my conditions, so it has to be random. I'm going to assume that the 53 subjects are representative of the population. It has to meet the 10% condition. So there are more than 530 subjects taking meds. And then the success failure, n times p hat and n times 1 minus p hat both have to be greater than or equal to 10, which they are. Now I can assume a normal model for a 1 proportion Z interval. And my work will follow this formula. So p hat plus or minus Z star times the square root of p hat times 1 minus p hat over n. I'm going to plug in all my pieces. P hat was 0.27. Z star for 95% is 1.96. And then plugged in p hat, 1 minus p hat would be 0.73. And n is 53. So if I take that value and I add it or subtract the margin of error, I get 0.1505 and 0.3895. So now I have to interpret all of this. So we would say that we are 95% confident that the true percent of people showing improvement from the new meds is between 15.05% and 38.95%. Our next example, we take a simple random sample of 95 Pasco County residents and find that only 20 of them approve of the new property tax to pay their repairs to local roads. Estimate with 99% confidence the true percent of people who approve of the tax. So n is 95. P hat is 0.211, so 20 out of 95. And my confidence level is 99%. My conditions, I have to have randomness, which was stated. So they stated it was a simple random sample. I have to have the 10% of the population have more than. There are more than 950 Pasco County residents, so meets that. And then the success failure, n times p hat, and n times 1 minus p hat, both have to be greater than or equal to 10, which they are. So the conditions are met, and I can use a normal model for a 1 proportion z interval. My work, z star for 99% is 2.576. Plug it into my formula. So it's p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Calculate that out, I get 0.1031 and 0.3189. So when I interpret it, I would say that we are 99% confident that the true percent of Pasco County residents who approve of the tax is between 10.31% and 31.89%. So some more information about margins of error. Things that affect the margin of error are the sample size and the confidence level. If we want a particular margin of error, we can set a level of confidence and a sample size in order to attain that margin of error. So margin of error is equal to z star times the standard error, which is the square root p hat times 1 minus p hat over n. So let's go back to our example about improvement rates on new medication. We found that 27% improvement. How many subjects will we need in a new experiment to make a 98% confidence interval while still keeping a 5% margin of error? Well, margin of error is equal to z star times the standard error. So my margin of error I want to be 5%, so 0.05 has to be equal to z star for 98% is 2.326. The square root, I know p hat is 27%, so I can do p hat, and then 1 minus p hat is 0.73, and I'm trying to solve for n. So I'm going to work out all the algebra pieces because it might have been a while for you guys since you've done this type of algebra. So I would divide both sides by 2.326. That would give me 0.0215 is equal to the square root of, when I multiply 0.27 times 0.73, I get 0.1971 over n. I want to get rid of that square root, so I'm going to square both sides. That gives me 0.004623 is equal to 0.1971 over n. And multiply both sides by n. I'm going to divide both sides by 0.004623. And I get n equals about 426.3. Well, we're talking about how many subjects, so people. So we would need 427 subjects since we can't have 0.3. Alright, so note, if we are not given a value for p hat, we're going to use 0.50. Okay, it's not really picking a side. It's not picking success or failure, and it also gives us the largest numerator than any other combination. So our first example with using 0.5 as p hat. What sample size must be used to estimate the outcome of a political election with a margin of error of 3% and 99% confidence? So they didn't give us a p hat value. So I'm going to use 0.5 for p hat. My margin of error was 3%, so 0.03. 99% confidence has a z star of 2.576. the square root of 0.5 times 0.5 over n. Okay, when you do all of the algebra there, you should get 1,844 people. All right, this example. What sample size must be used to estimate the true percent of left-handed people in the nation with 90% confidence and a margin of error of 8%? Assume that it has been shown in previous research that the percent of left-handed people was 38%. Okay, so I want a margin of error of 8%, so 0.08. A 90% confidence has a z-star value of 1.645. And the square root, they gave me the p hat value of 0.38, so times 1 minus 0.38 over n. So if I work out all the algebra steps there, I get n would be exactly 100 people.